In this lecture, we introduce a class of functions or transformations defined on the extended complex plane. These transformations are called Möbius transformations or linear fractional transformations. In this lecture, we are going to prove two well-known theorems regarding Möbius transformations. The first theorem is about the nature of inverses of Möbius transformations, and the second theorem is about the nature of compositions of Möbius transformations. Each point on the xy plane corresponds to the complex number z, which is equal to x plus iy, where I equals the square root of -1. X and y, of course, are real numbers. The extended complex plane is the complex plane with the addition of one point, the point at infinity. But what precisely is the point at infinity? We say that the complex number z tends to infinity when its magnitude or absolute value tends to infinity. The magnitude or absolute value of z is the square root of x squared plus y squared, or the distance of the point xy to the origin. Z tending to infinity means that the distance between z and the origin tends to infinity so that z moves away from the origin. Imagine standing at any point on the complex plane. The farthest that we can see is the horizon. We can march towards a specific point on the horizon, but we will never reach that point. This is true for every point on the horizon, and so every point on the horizon is the point at infinity. And so we treat all the points on the horizon collectively as one point, or we identify all the points on the horizon as a single point, as if we are collapsing the horizon into a single point. This is like gathering up the horizon and taking the complex plane with it, and then pulling the horizon tight like the drawstring of a sack and shrinking the horizon down to a single point. Think stereographic projection. A Mobius transformation f of z can be written as the quantity az plus b divided by the quantity zz plus d, where a, b, c, and d are complex numbers, with the discriminant ad minus bc not equal to 0. The discriminant being non-zero implies that c and d cannot be both 0 because otherwise the denominator of f of z will be 0, making f of z undefined on the complex plane. If the discriminant equals 0, then f will be reduced to a trivial constant function. In order to show that this is true, let ad minus bc be equal to 0. We consider two cases. Case 1, let cd be not equal to 0. And so dividing the discriminant by cd, we have a over c equals b over d, and we set these two equal to the constant k. And so a equals c times k, and b equals d times k. Therefore, f of z is reduced to the constant k. For case 2, let cd be equal to 0. Then either c equals 0 and d is not 0, or c is non-zero and d equals 0. Let us first suppose that c equals 0 and d is non-zero. And so bc is 0, and so is cz. And since ad minus bc equals 0, ad must be equal to 0. It follows that a equals 0 since d is non-zero. And so f of z equals another constant b over d. Now this time, suppose z is non-zero and d equals 0. ad will equal 0, and so will bc. Since c is not equal to 0, this will mean that b equals 0. And f of z equals az divided by cz, which is equal to A over C, another constant. And so to avoid mapping the extended complex plane to a single point or complex number, the discriminant must not be equal to 0. Now let us examine what happens at the point at infinity. If C is not equal to 0, and if z equals minus d over c, the denominator of f of z will be 0. But the numerator, which is a times negative d over c plus b, is non-zero, since ad minus bc is non-zero. And so the absolute value of f of z will tend to infinity if z tends to minus d over c. Therefore, defining f of minus d over c as the limit of f of z as z tends to minus d over c, f of minus d over c is infinity. We define f of infinity as the limit of f of z as z tends to infinity. Dividing every term in f of z by z, b over z tends to 0 as z tends to infinity. And so does d over z. And so f of infinity is a over c. On the other hand, if c equals 0, cz and bc will both be 0, but ad will be non-zero, so that a is not equal to 0. And so f of z, which is now equal to az plus b divided by d, tends to infinity if z tends to infinity, so that we define f of infinity as infinity if c is equal to 0. These take care of what happens at infinity, either with infinity as part of the domain of f, or with infinity as part of the range of f. The first theorem that we prove in this lecture states that every Mobius transformation has an inverse that is also a Mobius transformation. The proof is quite straightforward. Let w be equal to f of z, which is equal to az plus b divided by cz plus d, where ad minus bc is non-zero. We solve for z in terms of w. We leave it as an exercise for the viewer to check that z equals dw minus b divided by minus cw plus a. We call this f sub w of w. F sub w is the inverse of f for ordinary complex numbers except for w equals a over c, where the denominator of f sub w becomes 0. To verify that f sub w is the inverse of f on the extended complex plane, we must also check that the things that happen not just at w equals a over c, but also at infinity for f sub w are consistent with the things that happen at infinity for f. First, let's check f sub w of infinity. If c is not equal to 0, we divide every term in f sub w by w, and find that the limit of f sub w of w as w tends to infinity is minus d over c. If c is 0, cw will be 0 with a and d both being non-zero, and f sub w of w will tend to infinity as w tends to infinity. Let c be non-zero this time. D times a over c minus b will not be 0 since ad minus bc is non-zero, but minus c times a over c plus a will be 0, so that f sub w of w will tend to infinity as w tends to a over c. And so f sub w of a over c is infinity when c is non-zero. We still have to verify that the discriminant of f sub w is non-zero to ensure that f sub w is a Mobius transformation. The discriminant d sub w of f sub w is d times a, minus negative b times negative c. This is AD minus BC, which of course is non-zero. Therefore, f sub w is a Mobius transformation. For the second theorem, let f sub 1 and f sub 2 be two Mobius transformations. We show that their composition f sub 1 of f sub 2 is also a Mobius transformation. Let f sub 1 of z be equal to the quantity a sub 1 times z plus b sub 1 divided by the quantity c sub 1 times z plus d sub 1, and let f sub 2 of z be equal to the quantity a sub 2 times z plus b sub 2 divided by the quantities c sub 2 times z plus d sub 2, with their respective discriminants being non-zero. F sub 1 of f sub 2 of z should be equal to this tangled expression. Check that f sub 1 of f sub 2 of z is also equal to this expression. The discriminant d sub 1 2 of f sub 1 of f sub 2 equals this quantity times this quantity minus this quantity times this quantity. Multiplying out and simplifying, the discriminant is equal to this quantity. This last expression turns out to be the product of the non-zero discriminants of f sub 1 and f sub 2. So that the discriminant of f sub 1 of f sub 2 is non-zero, and the composition of f sub 1 and f sub 2 is a Mobius transformation.